Continuing with aldehydes and ketone reaction problems, nucleophilic addition, we have these three. So let's analyze what is our nucleophile, what's going on here in this reaction, particularly these two. So I want you to see this is a ketone, cyclohexanone, 3-pentanone, and we have reaction with an amine, primary amine, secondary amine. We also see that under the arrow we have pH 5.5. The reaction with amines, we need to have that pH control, and typically reaction rates have like a bell curve. In the max rate, if this is rate that we're plotting, and this is pH, between 4 and 5 we will have this maximum, so it varies. So we can say 5, 4 here, so 4.5, 5.5, around here. It has a bell curve. If normally we want to work at that pH, because if the pH is much lower, what will happen is that the amine gets protonated, and this is no longer nucleophilic. So that's why we want to keep that. And the fact that we have a little bit of acidic condition is beneficial, because if we have a carbonyl compound, we can protonate here at the oxygen. So this will make the carbon more electrophilic, and that with this nucleophile will work good. So that's why we have this control pH in the case of amines. So now what we're doing is nucleophilic addition, so nucleophilic attack. So here I'm going to do this. You can do that over this or over the protonated. Since we are in between at a pH that has that compromise, we can have that attack here or over to the protonated species. But we're going to do it like so. So the initial compound that you form is, let me make it a bit smaller. So I'm going to have O negative here. And now I'm going to have the N. And I'm going to have 2 H's and 1, 2, 3. That. So that nitrogen is positive. And then I need some proton transfer steps. I need to protonate here and deprotonate the nitrogen. After those, I'm going to do this proton transfer steps. So we're going to have any solvent mediated. So I'm going to form what we call a carbonyl amine. So this is NH and 1, 2, and 3. This is my carbonyl amine. All right. So what happened next is a dehydration step. So we're going to have a number of steps. And I have a video in which I explain that in detail, but we have multiple steps going on here. Basically, when you do proton transfer state, you're going to be dehydrating, and then you're going to be forming a compound that will have double bond with a nitrogen. But what is important, this is called an imine. But what's important is that in the primary amine, I had 2 H's. In one step, that was removed. And in other steps, the sequence step, the other H was removed. So notice I no longer have H's. So to get to the amine, I need to remove 2 H's here. That will be important because when we have a secondary amine, I only have that H. So the first part of the reaction is similar, and I'm going to draw the carbonyl amine. So I'm going to have O negative, so this attacking here. And so that is a common step. And again, to see more details on the mechanism, I have my videos on that. Please check those out if we need help. So now this is, I'm going to have, this is a 5-member ring. And I'm going to have this, the plus is not there. It's just an H. Ooh. Okay. And I need proton transfer step, proton transfer several. And I'm going to have the final carbonyl amine will have OH. And we'll have, I'm removing that. And what it means is that now I'm not going to be having hydrogens at the nitrogen. So I don't have that. And the following steps require that I do an elimination with other hydrogen. So in that case, what happens is that we eliminate one beta hydrogen. The product is then not an imine, not this double bond, but actually an enamine. So after removing water, after dehydration, so I'm going to do minus water. Here, minus water, proton transfer. So you're going to have a double bond here. And again, that happened because I had only one H. And that had already been removed here. And so that's one possible answer. And the other would be doing the double bond to the other side. So N, that's a 5-member ring. Only I'm squeezing it in. So you have two possible enamines. And here notice that at the vinylic carbon, here I have 1, 2 substituents. So this alkene is disubstituted. And this is, we have 2 substituents here and 1 here. So this is tri-substituted, and this is disubstituted. So most likely, this is major. Tri-substituted, okay? So pay attention then that if we have 2 H's here, well, we go to the carbinolamine anyways for the primary and secondary amine. But since you have here an extra H, you can form this, that imine. Lacking that H in the secondary amine after the carbinolamine, you will do an elimination with a beta hydrogen. And here you have position beta hydrogen here and here. These are the beta position. So you have 2 possible enamines. Okay. So this is the difference between that addition with primary and secondary amines. Now, the following reaction is not related to that. This is metachloropurbenzoic acid. So let's write the structure. So when you see that in the per acid, you will have an extra O. So say carboxylic acid, you abbreviate like so, and the per acid, you will abbreviate like C with 3 oxygens. Here it is. So this is per benzoic acid, metachloro, we have a chlorine here. And what this does is a Baeyer-Villiger oxidation. So essentially, it will insert an oxygen on this side or that side. So here we need to study what is the migration aptitude of the groups that are on either side here. So because this is like a rearrangement. So this is primary, that carbon. This is secondary. So the secondary has better migration aptitude. So you will insert the O to the side of the group that has better migration aptitude. So I'm going to remove this and do the insertion. So you're going to put simply an oxygen. So I'm going to do the carbonyl compound. This side stays the same, and I'm going to do the other side. So now I'm going to have a carbon. In that carbon we'll have a metal, and here you will have a metal. So that is essentially that you're going to be inserting. So remember that when you're studying, study the migration aptitude. Now, one tip here. Let's do one more of these with the A per acid. Another acid that we can have when you guys are doing problems is per acetic acid. So instead of acetic acid, you're going to put an extra O, and that's the O that you will be inserting. So if you had, say that I'm doing This is, now I'm going to put an H, and this is benzaldehyde. And say that I have, instead of metachlorobenzoic, I'm going to have, like I said before, peroxyacetic acid. So, that's that. And again, you can abbreviate it. You can see that in the problems drawn different ways. So metachlorobenzoic typically is seen this way. But per acetic acid, maybe you have this, or maybe you have that. Or, yeah, so it's structure fully defined or not, say, the structural formula. So again, this goes to migration aptitude. So to see to which side in this reaction, the Baeyer-Villiger oxidation, to what side we're putting the oxygen that we're inserting. So here you are comparing between the H and the phenyl group. And you guys check that out in your book. That H has better migration aptitude. So when you have an aldehyde, you always get a carboxylic acid because you will put the O on the side of the H. So here we go. So this side I leave the same, but now I'm going to put the O here. And voila, from benzoic acid I have, from benzaldehyde I get benzoic acid. So always, aldehydes will give you the carboxylic acid. Ketones, well, the side to you where you insert it depends.